This video tutorial presents a generic experimental procedure. Please consult your class notes for term-specific instructions. A clamped stainless steel ruler acts as the cantilever beam, fully constrained at one end. A strain gauge is mounted to the top surface to measure beam flexion. This simulation model illustrates the bending stresses along the beam length. From statics, recall the equations for a cantilever beam. Before any of the equations can be utilized, some basic parameters need to be measured, such as the beam width, beam thickness, and overall mass, which is conducted on the side table using a surrogate ruler. LabVIEW is utilized to measure the remaining parameters. Open the LabVIEW shortcut folder and select Vibrating Beam CDAC. Once the LabVIEW program opens, navigate to the Configuration tab. The test duration defaults to 5 seconds with a sampling rate of 2000 Hz, but both may be edited per the term-specific instructions. The next parameter to define is the elastic modulus. Gently position the beam to a preselected length and clamp securely, careful to not touch the strain gauge. In LabVIEW, select the Static Test tab. Then click the Run button along the top menu bar. Verify the beam has settled, then click the Null button, followed by the Calibrate button. Now click the Take Data button to measure the strain of the unloaded beam over the specified test duration. The default is 5 seconds. When finished, save the results to a data file on the desktop. Be sure to select a descriptive file name. Hang a weight on the beam end to apply a known load/stress. Once the beam has settled, rerun the LabVIEW program to measure the resulting strain and save the data. Continue to rerun the test while increasing the load and save the data to a file on the desktop. Do not exceed 200 grams. Ultimately, the stress-strain data is plotted to determine the elastic modulus of the beam. With the static parameters determined, let's investigate the dynamic behavior of the beam. Reposition the beam to the desired length and clamp securely. In LabVIEW, select the Vibration Test tab and then click the Run button. Once the beam has settled, click the Null button followed by the Calibrate button. As previous, click the Take Data button to start data collection. Immediately apply an impulse load by tapping the beam with a pen. Observe the damping effect as the oscillation amplitude progressively decays. The dynamic response is displayed along with an FFT across the Nyquist frequency domain. The dominant frequency is identified along with the FFT resolution. When finished, save the results to a data file on the desktop. Be sure to select a descriptive file name. The data file lists the test parameters in the header, followed by the time-dependent measurements, which may be imported into MATLAB or Excel. Rerun the test while progressively changing the beam length. Be sure to save the data files to the desktop. Use the data to plot natural frequency as a function of beam length. The damping coefficient is determined using the dynamic response data. In a nutshell, you'll need to measure the progressive decay in amplitude between successive peaks. Your instructor may have you investigate the effect of a lump mass on frequency. Typically, one or more magnets are placed at the free end. The dynamic test is repeated to generate a modified plot of frequency versus beam length. The magnets are extremely brittle and will easily shatter upon impact. Remember to save your data before leaving the lab today.